Hi everybody, I'm Meenal Satyagarkar. I work with Arcadis as a design engineer in rail structures. I primarily work with steel structures for station buildings and bridges. And this particular webinar is design of steel structures using STAAD. I'll try to cover a STAAD demo, a small one, if possible at the end. But the motive of this webinar is majorly on what is design of steel structures, what are the phases involved in design of steel structure, how a design can be classified as a good design, and what are the things that make a design a good design basically. So let's start with health and safety moment. So we generally start our meetings with a health and safety moment. It's basically trying to get your attention to something. And today I pick something you might be aware of, the Tacoma Narrow Bridge collapse. If you haven't seen this video, please do Google it. You'll see how this bridge collapses due to the wind. And basically, it was a close save for this person whom you can see on the screen. But a bad design can cost lives and money. Money is fine. It it's still recoverable, but something like a life cannot be measurable. So you have to be very vigilant while designing any structure, any civil thing. And that brings me to one important question: who is a good designer, and what is a good design? So whenever I meet people who have a lot of experience, I do ask them, what is a good design? How can you say that this design is a better design, or who is a good engineer? A lot of time during our colleges, we are so much deep diving into the mathematics of it. We kind of miss the softer aspect of designing and engineering. A good design is defined as something which is constructible, economical. Constructible is something which is very minor, but say you have to put a bolt inside and your wrench cannot go in, then your mathematics can be correct, your numbers will be right, but your design is a bad design. It's not constructible. Or if it cost you like it should cost you 10 rupees, but it costed you 20 or 30 or even 50 rupees, then it's a bad design. It should be well coordinated. If you don't think beyond, I don't know how many of you have seen roads being constructed and then immediately getting dug into to put a cable in. That is a bad designed road, and we as engineers are responsible for it at every aspect of it and cannot blame it on the governance. We have to plan, we have to make sure that our designs are coordinated, they are suitable, sustainable. They should be safe to build, operate, and maintain. As I said before, that a bad design can cost life. So if you are building something, it should be definitely safe to build as well, not just for someone to reside in it. It should not fail in construction stage. So you have to consider the construction stage analysis and be quite vigilant about the hazards that it can cause. Say you have a site which is close to a school, and obviously you want to prescribe a design which is less noisy, so that so the students in the school don't get disturbed too much with your designs. So these aspects are also aspects of good design, and as a designer you have to be aware of all these things. And one important thing that has come up recently is the sustainability part of it. So a good design is also sustainable design. Now, sustainability itself is a huge topic, and as human beings, we have caused a lot of harm. So we should see how our materials are procured. If there is a lot of transportation involved, we should try to cut down on these things while designing itself. So a structural engineer, although it looks like very mathematical job, try to understand it also has all these, I'll say, smaller points, finer points attached to it. And these are very important points to keep in mind when you are designing any structure. So, yeah. So a good engineer is one who designs good. Again, there are different stages of design. As I was saying, there are stages of design. So when we are studying, at least when I was studying, a lot of all kind of attention was given to detail design. So we'll be learning how to calculate the bending moments, the shear force, how the interaction goes, and then how what all design features, the codes, how to apply the codes in your design, what is length and breadth and width and everything of that. But that is only a part of design. I'll say when you start working in the industry, you realize that is only one part of the structural design. Now, if I start, the design actually starts with a design brief. So when a client comes to you, he has something in mind. Say we work a lot with UK projects, and we have something called AFA or SFA. So step-free access or access for all. These are basically the stations that go under renovation so that people with disabilities can access the station as easily as someone who doesn't have any kind of disability. So that is a design brief. Now, all station can install lifts and footbridges and whatever to make it AFA or SFA, but it cannot be that every option is feasible. So it goes under feasibility. I'll not talk much about feasibility because it majorly comes never to us. It's a different team that does it. Our work starts from optioneering. So what is optioneering basically? This is the design phase where we as engineer decide which option is a suitable option. So it depends on a lot of things. What kind of option the client is looking at, one thing. Other thing, what kind of structure you have to build. Say if you have to build a bridge, what is the span of the bridge? What is the length of the bridge? Do you want to work with concrete or steel or timber? So a lot of options are dwelt into. Client is presented with a lot of options, and then you decide on, okay, I want a truss bridge. And then even in truss, you can go with, if you want a king span or you want a verandel truss, or what are the preferable options, where is the crane and all these things. And you can decide on either you want a concrete bridge or steel bridge or timber bridge, what kind of structures are there existing in the vicinity. So you can pick the similar kind so that it doesn't stand out. It can be some architects are involved and they want a particular kind of structure. So all these things come under optioneering. Once the optioneering stage is freezed, you'll know what kind of structure you are looking at. Are you looking at a concrete structure or a steel structure? If steel, is it a truss structure or is it a integrated beam kind of a bridge? Or do you want some kind of trusses, or you want verandel kind of truss? So, or you want a closed structure or open structure? All these things come in optioneering. And this stage specifically is very based on previous knowledge and do not involve a lot of calculation. So these are the things that experienced engineers do. They just preferable options they can bug through and see that, okay, this bridge is a 7 meter span. We don't need huge a huge structure for it. Giving a cable tray is just stupid idea. And if it's a very big structure, say 700 meter span, then what do you want to go with? You want to go with a cable stayed bridge or a bow arch bridge. There are varieties of it. If you go to your textbook, you'll find what kind of options can be used. But then it also comes with the economy aspect of it and how much client is ready to pay for all this. So a lot of time you might come across clients who want some landmark structure, and then they are ready to pay a lot of money. in that case, you have to design or give options which are really beautiful. But there are most of the times you might come across that you want the most economical solution going through. Then obviously you pick the economical ones. Once the optioneering phase freezes, we go in preliminary design. The preliminary design or concept design is what we pick from optioneering. So now we know that we are going to design a steel bridge, a Verendel truss, say, and what's the span of it. That kind of things are fixed. So what we are giving is the 30% of design. The 30% of design, what does that mean? Is we'll be generating drawings, we'll be generating um, drawings without much of details. What that means is, say you are saying that you'll be using an RHS section for the main member, but you'll just write RHS 300 by 200. You'll not give the weight of it. If in case RHS, I'm not very sure. So I work with Euro codes majorly, and I'm not sure if that's the same terminology used in IS code. But RHS member is nothing but a hollow section, rectangular hollow section, and you'll not define if it is a 10 thick plate or 18 thick plate. You'll just give a design that is kind of giving a overview of the design, possible design. And it, the main things that you want to give in the preliminary design would be, say, what kind of elements you are planning to use, what kind of span is there, is it 6 meter span or a 7 meter span, and other things that would be there is the total load that you'll be expecting on your foundation. So someone from the geotech can also give you a tentative design for your substructure. So it could be a pile foundation or an open foundation. Again, they also have to do their own optioneering and with the reports available with them, or if they need some other kind of reports, they can ask for it from the client. So this all is done with the preliminary design. Preliminary design, it also involves a lot of coordination with architects, MEP, drainage, and electricals. Kind of miss that. Okay, so everyone has to be in coordination for a preliminary design to work. That is the basic idea of having a preliminary design. We don't want people to have something at very wrong places and then struggle at the end. And preliminary design also fixes general method of construction. What will be the lifting capacity of the crane that will be used, where can we mount the crane. So I work with railways. A lot of time you have an existing station that we are working on, and we don't have access to the station. Then what is the place where we can put our crane, how much is the boom of the crane, where it can reach, how much is the capacity of the crane at that angle that it can lift. So we have to divide our um, elements into smaller. So if we cannot lift the whole bridge, we'll lift it in two parts and lift it and everything. Whatever comes in, we kind of lift, decide on that. And but preliminary design specifically doesn't give design of secondary members, detailed design of the main members as well. As I thought, as told before, that RHS 300, 200 will be enough. You don't need to give it the thickness of the element and all. A little bit of change in detail design will happen, that is accepted. A lot of change is not acceptable. Another thing that it does not include is the connection design, the weld or the bolt design, and also not the reinforcement detailing if you are going with the RC for foundation or yeah, this is specifically for a steel building. The reinforcement detailing is not involved. For a concrete building, concrete structure, reinforcement detailing is involved, but it's not a detailed reinforcement drawing that they are expecting from you. During the preliminary design, there are certain things that I really want young engineers to understand, and one of that is design risk assessment. Whenever you design it, as I said, it should be very sustainable and it should be friendly for the people who are using it or people who are in vicinity of it and people who are building it. So every design should have a risk assessment. Now Risk assessment necessarily means that you define what all risk you can think of. Say for, as I said, when we work in railways, we have very important risk, that is working near the rail line. You cannot avoid it. But how to mitigate it? So one idea is to put a hoarding kind of a thing where trains or people cannot come inside the site. But you have to define it right at the start of your project in the preliminary design so that it is accounted for. One very common risk is, say, falling from height. People will be working on height. Your bridge is higher, your lift shaft is higher. Anything beyond 3 meter is a dangerous height to fall from. And how do you mitigate it? You put it there, and you try to do whatever work you can do on ground and then lift it up. So if you have a cladding to put the cladding first and then lift the structure, rather than putting the structure first and then putting the cladding on it. This is the way we mitigate the risk. And this should be highlighted on your drawing. So whenever it reaches the site, it should give the idea to the site engineer that this is how it should be. It should be built. How you want the cranes to operate. If there is some kind of demolition to happen, what are the kind of temporary supports required? All these things should be captured and reflected on the drawings. So as an engineer, you are responsible for any kind of uh, accidents that happen on site because of not stating these hazards. So these are the hazards that you should be aware of and you should think about while designing during your preliminary design itself. Don't wait for the end of the design to find out if it is a problem, because there are certain risks that you can mitigate, certain you cannot. Say working next to a railway line, you cannot do anything about it, but working at height, obviously you can put all the cladding first and then lift it up. It is a hazard mitigated. So and then again, the severity, if you see on the screen, there is a table that says risk description, likelihood, impact, severity, owner, and mitigation. Now severity again is also dependent on the money involved, or the fatality that can happen or something like that, and we try to reduce it as much as possible into medium or low risk and not go beyond that. In circumstances it is unavoidable, you have to communicate it properly to the site and get it registered in their understanding. During preliminary design, one more thing that comes in is level of detailing. Nowadays, you might have heard some about BIM. So BIM is nothing but building information management. That's what they say it. And there are other acronyms used for it. Kind of connects all the disciplines together and build a kind of an environment where your design can flow freely. With that, level of detailing comes is an important aspect. Even without BIM, it's an important aspect. Sometimes client is looking at LOD 200. There's no point in producing LOD 350. You can see on the screen what is LOD 100, 200, 300, and 400. It's kind of the progression of drawing from, say, LOD 100 will be your very optioneering stage where you are just space marking something. Okay, there will be a column here. You are not even saying it's a beam or a UC or RHS or anything. But when you come to LOD 200, you say, okay, fine, this is a UC column. And then when you go to LOD 300, you define that, okay, this is column with 150 to 152 UC, and then LOD 350 you'll also define the base plate for it, and there will be 4 bolts. With LOD 400 you'll give all the details of the column along with the foundation details properly done. So you need a lot of effort to go from LOD 100 to 400. A good designer understands where he should stand at what stage. If you are expected to give LOD 200, do not try to give 350. It will not be economical solution. And it might be that this particular solution is not accepted, then all your effort goes in vain. So that is something called level of detailing. I'm not okay. So these were the two concepts that I wanted to highlight in preliminary design. There are other concepts as well, but due to the time I haven't touched everything. But yeah, found this interesting for new learners. Where we come is detail design. Detail design is the stage that we generally study in our curriculums. We submit 100% of designs and drawings, obviously. So detail design involves all the design of main members, coordination. It involves general method of construction, nicely written and printed, design of secondary members, connection, reinforcement, and RC design and everything. It's a whole package, and the package should be in form of drawings and calculation. Try to understand that even though structural engineers, they deal a lot with the calculation part of it, what is more, you cannot neglect the drawing part of it. At the end of the day, it's the drawing that goes on site, it's the drawing that interact, and the calculations are not open until it's a necessity, and they are more like a documented proof of the design that works. So the drawing should be well coordinated and should be something which, when a site engineer opens, he should be it should be easy to comprehend, and it should not it should be built for him. Most importantly, built for him in sense keeping him in mind. So say you have a very simple lift shaft drawing, and you have four drawings for it. One is the steel drawing, another is the connection drawing, and then you have to give the foundation drawing for it, and you have the reinforcement drawing. Imagine if you so typically what happens is your foundation is casted by some other contractor and your steel work is done by the fabricator who develops the fabrication drawing based on your detailed design drawing. So the fabricator has to develop his fabrication drawing. He is not concerned much about the reinforcement drawings. But if you haven't segregated the drawings properly, he will have to deal with your reinforcement drawing unnecessarily. So you have to be mindful and thoughtful that what is the purpose of this drawing? Why am I producing this drawing and to whom I'm sending this drawing? All of these things, when you think properly in start of project, then you have something called a TDIP. The TDIP is nothing but the number of drawings and documents that you produce, and you number them, you give them a nomenclature, you give them names and all, and the title block gets filled, and accordingly you put your details on the drawing. So the drawing, if you are thinking about the end user and producing the drawings, it will be a much better package than if you haven't thought about all of these things. The same thing goes with the coordination. If the drawings are not coordinated properly, if your architect's drawing and your drawings are not matched, and site has to come back again and again to you asking for changes, asking that they model they put a post and now your column is coming out of it and it's not fitting in, or things like that, then it's a problem at your end. It's your mathematics is correct again, but it should be coordinated. It should be good for the site for MEP drainage and everything. With BIM coming in these days, the 3D modeling part, it has, so I'll like to tell you that these have become kind of a necessity in this new era, and you have to learn about the BIM, the 3D softwares in the system, not just for structural analysis and design, but also for modeling it and creating models that can be shared, that can have a shared platform between interdisciplines, can be shared to clients, can be shared to site, so that you understand it. um, I'll run you through STAAD Pro in a minute. These are the stages in detail design using STAAD. This section is specifically for STAAD. I'll come back to this section. This is how a window in STAAD looks. Most of you might have used it. It's a very user-friendly software. You need to have basics right, and it will just help you out do the design. One important aspect in detail design is clash detection, as I was mentioning. So because we have 3D software, say Revit, or we have EcoSim from Bentley, we have very good understanding of how things can mess up on site. So we have this clash happening here. Now, if you see this, if this is a beam and this is first 1/3 of the beam and there is a pipe going through, I don't want my beam to have holes here. I'll prefer the holes in the midsection if it's simply supported here, because the shear is not there and the web is not participating in web doesn't have to take the shear, so I can accommodate this pipe here. If I know this early on, I can move it. If it goes to site like this and it's not well coordinated, site can put a hole in this on basis of the drawing from MEP, and then it's a problem. Or say something like this where your drainage is clashing with your fire pipe, and this cannot happen. So you have to either move your drainage or you have to move your fire pipe, and you need a lot of coordination between different disciplines to get this done. There are certain other examples here what you can see. Again, some discipline has to move something up and down to accommodate it and make it right. If this kind of thing goes on site and they cast one which was to be moved, then it becomes a problem. And again, it results in money. Or if it's a major error like this, if they might have put it here somewhere where the shear, it cannot, where the beam cannot take the shear after the hole is punched through, it can cause a lot of money or even lives, which we don't want. So yeah, keep in mind the clash detection, keep in mind the coordination. It is very, very important aspect of a drawing, as important as the beam design. Okay. And then there are ancillary structures. Although small structures here and there, but always think, are they really ancillary? So you have an existing masonry wall that you want to knock down. So be aware what kind of loads it is bearing. Are you ready for that? Do you have enough data to support whatever you are doing? You do keep asking the right kind of questions. They'll take you to places, because it is very easy to miss on these points. The geotech report, have you studied it properly? Do you know the capacity of soil where you are working? it it's just not the numbers. It's also about how well you are asking the questions that are very necessary to be asked. Sometimes you don't have the data. Do dig for data. Do not assume things when you don't have the data. Assuming things can again cause a lot of money and problems. Okay, so uh, this is London Bridge Station. This is an old building, how it was, and now it looks something like this. Um, this is a case study for some reason. Okay, the reason being, I'm gonna show you the website which shows how it came in this shape. Okay, the link, I can give you the link for the site whenever it's up and running. You can just go and see how it looks now. Anyways, I have that photo there. So you can see it looks like this now, and it's a massive, massive work that was done recently, and all uplifted, given new looks. The London Bridge Station. And how much time? Okay. Manvita, how much time do we have?
I mean, no, you can continue. Yeah.
Should I open up the STAAD, or you want to continue with the question or answers, anything like that? So this is how a STAAD looks. The interface of STAAD is this. When you open it, there is, if I go back to my presentation,